Hey, I'm Jesper Kristensen, and in this video, I'll teach you how to create an ERC1155 in pure Yule. Learning to create an ERC1155 in Yule is helpful because knowing how the ERC1155 works at a very fundamental level, which is almost assembly, right? Yule is very helpful because you'll get to know the inner workings of an ERC1155. You'll get to know everything that's going on behind the scenes in terms of the stack and memory and so on. 2, you'll be able to implement one yourself or even other tokens. The ERC1155 is pretty complicated, particularly around dynamic types, which is particularly challenging to write in Yule in general. So it's a good way to really get to know this code. And then 3rd, just getting you more familiar with Yule in general. Being able to write Yule is extremely important for any development in Solidity, because you can always open up an assembly block wherever you are and start coding and have much more power and be closer to bare metal, so to speak. If you have any questions while watching this video, please let me know in the comments. And also, if you find the content helpful, please like and subscribe to this channel. Let's jump into the code here. As mentioned, the first thing that I would highly recommend you do is to, make sure that you can compile your Yule code. Okay. So what I mean is, when you normally develop in Solidity, you have Hardhat, you have Foundry, some other tools, Truffle, etc. There are many tools out there to develop in. Those all comes with where you can compile your code. So far, so good. When you write entirely in Yule, the compiler gets a little bit more sad if you just throw pure Yule code at it and say, please compile this, right? Because it's not so used to it. However, it's not that difficult either, but I just want to highlight that. That's where I would start, and that's where it did start for this project. So what do I mean? I mean, you can see we are in a project here, right? I have it open in Visual Studio Code. These are the files in here and folders. So first thing I'd want to do is create a way to just, what I would do if I were you was go into contracts here, create your ERC1155 Yule or whatever your contract name is, right? .sol. I do the .sol for the highlighting. Okay, VS Code will give me nice highlighting. You see the colors and everything in here. That's because it recognizes .sol files. If I changed it to .yule, it would not show me the highlighting. And in fact, the file extension name does not matter. At the end of the day. So, okay, so this is the ERC1155 Yule. What I would do if I were you was create just the object. And I covered this in a previous video I did on how to program in Yule. I covered like the structure of these files. So the structure is you have this object, you give it a name. That's kind of like contract. And then you give it a name in Solidity. And then you open with curly braces and you close it again. And this entire file, which I'll go over in a second, you see it ends, that's it. It's just the object here, opens and closes kind of like a contract, right? And then there's a code section. So within an object section, you can have a code section. And this opens and closes as well. Now this happened to be the constructor part, this code. And you can have another object within an object section. And this is kind of like, also like the contract, right? So this overall object here is like you have the constructor with you. And the constructor at the end of the day, when it comes down here, deploys what is tagged in the code and called deployed, which is this piece here. We'll go over this in a second in more detail, but I just wanted you to know the structure. And then you can have another code within the object and so on. And that contains the main code of this contract. Okay, now my point with saying that is, if I were you, I would just start with a very simple thing like object, my contract. So this is whatever you're writing, and I would just open and close it. And maybe even have some constructor code if you really want, where you can just return, okay? You can just basically return, you don't even need this. You can just return 0. And the data size, I mean, you can just say it's something or maybe even 0. In fairness, I haven't tested this exact. This is a very extremely small code, but the point is you write something that's extremely small and just like a proof of concept just works. And then you move on to immediately after, before you dive in. It can be tempting to dive in and start coding everything, but you don't want to be surprised later that, oh, you should have done something differently to compile, or you need to do change a lot of things, or even do another project setup and so on. So immediately after you've written this, we can just use this now, but you would have a smaller version, go on to compile it. So under a compile folder, I have a compile.js file. This is a file that imports other files. Each of these files, these are helper files. I'm compiling a contract that's used. I'm compiling a pure Yule contract. Okay, so I import these things. These are the other files in this folder. And then what I do is I basically just describe the input to the Sol-C compiler. And I just say, hey, the source is actually this contract, ERC.sol. The content style is source, and so on. And then I have a settings, please output the bytecode for me, when you're done compiling. And so I get that in return. And I compile another code here, which is no receiver.solidity. We'll get into what that is. It's about whether you're receiving an ERC1155 or not, and then the receiver. So all these three sections are just compiling one code, one separate piece of code. The help, let's take a look at the helpers here. Those are the ones that are doing the actual work. So you can see it's a function called compile ERC1155 Yule contract. That is the one I imported over here. And that is the one that I then call against this input. The input just points to which, first of all, importantly, the language, which language I'm using, which is Yule. Normally, when you compile Solidity, you'd put Solidity, of course, but now we put Yule. So there is that option for the Sol-C compiler. The source is then the contract you want to compile, and then you pick which output you want. I just want the bytecode. Normally, you can maybe even get more stuff out, but it's not relevant here. We just want the bytecode. Okay, now what does the actual compiler itself do? Well, here we just make sure that any existing compiled files are being deleted. And this is the meat of it. We call Sol-C, which we imported here. So we've installed Sol-C. And then we just call .compile against a stringified version of the input. The input comes in as a parameter. This is the one that came in right here. Okay, right here. So that's the input. As you can see, there's a JSON right now, but it gets stringified. And then that's it. The output will be the bytecode. So what you need to do is you could have multiple contracts. So as you notice, I split this into 3 separate compilation steps. There's no need to do that. I could have done everything in one, but I just wanted to do it for clarity, especially for such a small project as this. It doesn't really matter. But the point is you can go in and fetch which contract you actually want to get out. Now, in this case, again, we've only compiled one contract, and this is the name of it. So we just get that one. And then we go into, this is the file name rather. I meant to say that. This is the contract name. They're basically the same, except of course the contract name doesn't have an extension. And then you do .evm, so you go into the EVM section of the compiled output, and then you get the actual bytecode, meaning, the 60, 40, like the actual numbers and whatnot, right? Underneath everything. Good, once you have that, you're done. You just write the file, this is what I'm doing here, and I throw an error if there is an error. There's the callback function defined here, and if not, then I just lock something to the user that everything is fine. Okay? That is how, and by the way, all this code is available in the repo, publicly available. Just go and clone it, go and take a look at it yourself. But this is one. I do the exact same thing for the other contracts that are also written in Yule and even, Solidity, actually. You see here? The others are written in Solidity, rather. So the first one, Yule, this one, Solidity. The reason I'm putting everything together, even Solidity in here, is because if I have a mix of Yule and Solidity, the compiler, hard hat, for example, is going to complain, oh, you have a mix of things. So I just decided to convert everything to one compilation format, which is this one. Okay, great. So once you can compile, that's a good first step, right? Now you can actually compile your code. That's great. Now I would test, again, even before writing anything, if I can deploy. So the way to deploy is, by the way, when you compile, I forgot to mention, I highlight that, but when you actually write this file, what is the path? It goes under the build folder, like the compiled output goes to the build folder and goes into a file called .bytecode.json, okay? So in the build folder, this is what you see here, .bytecode, it's okay? And you see this object here, this is all what I was saying with the 60, 40, and yada, yada. This is 61, 00, 18, and so on, right? And these are the actual instructions for the EVM, not shown in bytecode, but shown in essentially these instructions. Okay, great. So that's what that is. On top of that, you also have an API, and this depends on your contract. At the time of this recording, the compiler Sol-C is not clever enough to give you the API of a Yule contract. So you need to manually write that. I showed you how to do that too in my last video. But now you have the API, you have the bytecode. Okay, those need to match for optimal experience here. All right, so you compile, you get the bytecode, you get the API. Now you go to deploy. Deploy loads the API. It loads the bytecode, as you can see, and then you can actually still use hard hat, and you can get the contract fact. You can just call get contract factory, but instead of just calling it by name as we would normally do when we do hard hat compile, now we need to just specify the API and bytecode. This is also very cool because it does actually mean we can deploy arbitrary bytecode, right? It doesn't need to. I mean, it could really be anything. So yeah, we can do that. And then here we call deploy against that contract, okay? And we need to give it a constructor argument. I'll get into that later. This is an ERC1155. So what we're gonna do is just give it the base URL from the documentation where this ID needs to be implemented by the implementer, in terms of, being able to essentially input that ID in place of this template string here. Okay, we wait for it to be deployed, and that's it. Fair enough. So I would test those things. Again, I would test those things against essentially a skeleton Yule contract first. Don't even get started developing the actual Yule contract. Make sure you can set this up. And in fact, since I have this code for you, just clone this repo, take this code, and start writing your own Yule contract, right? Just delete everything I did and do another one if you want to. And everything is set up for you, right? Just confirm everything compiles, everything is fine. And in fact, in the README, I have some notes as well on what I did here and how you interact with this. Okay, now we can compile, we can deploy. Let's also make sure we can test. So I did write a test for this ERC1155 so that I'm ensured everything works as expected. So you can write these tests as well, of course. You just need to get the API, the bytecode, get the contract factory, deploy this in your test, and that's it. It's deployed. And once you have deployed it, you can interact with it like anything else. You can make sure it got deployed to a valid address. You can call functions against it. Here's a function called URI. Here's another one called mint. Here's another one called balance of. I'll get into those, how they were implemented in Yule. But the point is you can test everything. So I would also set up the tests and just make sure, of course, there wouldn't be any functions because it's a skeleton code, but at least make sure it gets deployed, right? Make sure the address is a proper address and not null. Once you have that, so once you have the compile, once you have the deploy, once you have the test, you're good to go. We can start coding. Now you won't be surprised down the road. And in fact, this also leads you to be able to test or build in a very test-driven development style so that every new function you add, you can just immediately go over here and add a few tests for it. You can see I added a bunch of tests here for the full contract, like about almost 775 lines of tests of various functions that I implemented. But it's always so nice to do a test-driven development. So what is that? It's just that you essentially write your tests almost before your functions, right? Or at least like very simultaneously with, if I may be a little flexible in the definition. So basically, I don't build the contract and everything, and then I go on test. I essentially do it, at the same time / even write the test before. So so how would you write a test before? You would say, well, that when I mint a token, the balance of should be 0 before I do it and should be 1 after I do it. Things like, so how the code should behave even before you write it, right? Okay, great. So good. Let's actually dive in. I think this is a good time now to dive into the actual code. We're ready for that. Yeah, so good. We have an object called ERC1155, and we appended this Yule because it's written purely in Yule. What we're going to do is we're going to have, and all these Yule contracts, there's going to be a constructor section, at least if it has code. So the constructor section is what the miner calls when they actually create this on the blockchain, this code, right? They call the constructor. The constructor at the end, when it's done, essentially sends a message back. It sends a return value back to the caller, like the miner, that says, hey, by the way, the code you need to deploy is this big, and it's located here and here in memory and whatnot. And then the miner will go in and actually take the code and deploy, basically in like where the code lives, right? In the code slot, so to speak. Okay, cool. So this is the constructor. Even during construction, we're going to have some helper functions. We're going to define an owner slot. So that just means this is a pointer essentially that points to where in storage we want to store the owner. And we also have some other pointers, P1 and P2. We're not using them here, but this is just to tell you why we're jumping to storage slot 3 in the next defined function. That is because technically the storage layout is like this. So we just wanted to mimic the, like we have to keep the storage slot fixed between this and the main code. So we also store in slot 3 here, URI length slots. That's the length of the URI that's associated with this ERC1155. Okay, now, so what we do is the caller, which is whoever, called, like created the contract, right? So whoever created this ERC1155 to begin with, constructed it, right? Will be stored in the owner slot, which is in storage slot 0. Okay, but notice how this general, if we change this to 1, this code will still work, right? It'll still call owner slot, which is great. And then we're also going to store the URI length, which is the length of the incoming URI that you give it. Now, in this case, I actually went ahead and hard-coded the URI, but this could be generalized. It's a little bit tricky around Unicode and whatnot to make it work with that, but it can be done. I just decided to hard-code it to the string you saw outside. So you did see the constructor argument I showed you before. That's actually technically not necessary because it's hard-coded in here. But basically what happens is we're storing here the length of the string in bytes, and then we're just adding in the next slots. You can see we add 1 to the slot, like to where the length is stored. There we store the beginning of the string in hex, and then we keep going until we end right here. So over the next 2 slots, right, we add 1, we add 2. So in the next 2 slots, we store the actual string. So that's typically how these dynamic things like a string are stored. You have the length in the first slot so that the computer knows how far to search into the future. And then you have the actual string stored afterwards. Okay, and then we deploy the actual contract here. So what this means is just we send the code that is the actual runtime code, so to speak, not the constructor code, the runtime code. The runtime code is what this is. Okay, we send that back. We send the size back to the miner so the miner knows where to go look for it and deploy it. So we basically copy the code into memory, okay, starting at slot 0 in memory. And then any offset that is necessary to get to this part, and then the actual size of it, okay? So we're basically saying, okay, out of all this entire code, like go to the offset where this code starts. And this is nice that it has this tagged. You'll has this kind of, you can tag these sections, right? So I don't need to manually compute the offset, right? Because if I keep changing the constructor, the offset would keep changing and whatnot, but I don't need to do that. I can just say, just give me the offset of deployed. And from the offset, get the size of all this code here, okay? Only this code. So this whole thing, I'm going to copy into memory, and then I'm going to return, starting from 0, just the size of that code that I just copied from 0 to the size, right? So that just means I'm returning the actual runtime code. Here I called it deployed, but sometimes you will also see this called runtime, like this, because it's a runtime code. Okay. So that's what the constructor does. So pretty easy, right? Okay, anyway, the miner goes ahead and just deploys the actual runtime code. That means the constructor code does not get added to the blockchain, okay? So if you didn't know that, you know it now. You can see that here. What the constructor does is just take the runtime code and then it returns it to the miner. And this will not get deployed to the blockchain. It's only the runtime code. So for the runtime code, we're going to have a storage layout that we already alluded to in the constructor. But basically, we're going to have the owner in slot 0. We're going to have the balance in slot 1. We're going to have the operator approval in slot 2. And that's just, someone approving the usage of the token for someone else and whatnot. And then we're going to have the URI length in slot 3. Okay, so this is the storage layout. Secondly, okay, when you write UL, it's very helpful to kind of mimic what Solidity does, which is having a free memory pointer behind the scenes that you can interact with. So it's just a pointer to memory where your next free slot is and where you are. So imagine every time you add something to memory, you just advance this pointer and it will always point to the next available slot for you so that you don't have to manually keep track of anything. It gets a little bit difficult over time. So basically, what I did was try to mimic the Solidity structure where I created 3 scratch slots here. Gets super helpful when you have to hash things later on. And then there's the memory pointer that sits in slots 0x60 to 0x80. Okay. And then I have some helper functions later on that can help you get the memory pointer and set the memory pointer and advance it and so on, which I actually found very helpful to write just as I went through the code. So first available memory slot is 0x80 because the pointer itself occupies 0x20 or 32 bytes between 0x60 and 0x80. So 0x80, that's the first slot available. So you can see that here we're actually calling a function. It's a helper function that I wrote that I'll show you in a second. I'm setting the memory pointer to the memory pointer position, okay? And then I add 32 bytes to it, or 0x20 hex. So in other words, it sits at 0x80 to begin with, okay? Good. So let me show you the memory pointer helper function. So I'm going to scroll down. Towards the bottom are all the helper functions in general. So yeah, so you can see here, memory pointer position sits in 0x60, right? It occupied 60 to 80, so that's where it sits. Getting the memory pointer just means loading, so loading from memory, the memory pointer position, which is 0x60. Setting the memory pointer just means it takes an input v, and it basically just stores, so it stores to memory, at the memory pointer position, the value v, okay? So it just means I'm gonna set a new value for the memory pointer. It's still gonna be stored in 0x60, like the location doesn't change, but the value of it changes, meaning where it points to changes. It always points to the next available, memory slot. I also wrote a helper function called increment pointer. So it basically just takes the memory pointer and adds 1 slot to it, or in other words, it adds 0x20 to it, or 32 bytes to it. I also created like some safe add and safe subtraction. So this is basically, it also handles overflow conditions. So you can make sure that, it doesn't overflow. Okay, so we have that memory pointer. This was a lot of fun to write. Once you have the memory pointer, that's a very powerful tool because we're gonna have to be doing a lot of things in memory. Memory is a nice kind of space to do things like hashing things, like when you call catcheck and whatnot, it happens in memory. So the stack is the main thing that, you can think of a stack of plates that has these operations that you're doing. You take plates away and you add plates back on and you do operations on the plates and whatnot. And memories is a place where you can kind of store, it's like a big array where you can store all kinds of values. All right, cool. So here we're just going to ensure ETH is not sent to this account, like basically to the smart contract. So we're going to get the call value, which we covered in some of our hacker videos as well. But call value is just how much ETH was sent to this smart contract. And we're going to make sure that it is 0. We're going to require that. Okay. And now we come to the actual meat of the contract. These are the actual functions like mint and balance of and URI and whatnot. So what this means is, we're first going to get this function selector. So someone sent a chunk of data to our contract. It's just a bunch of hex characters, right? We're now going to go in and get the function selector. That has to be the first 4 bytes. We're going to extract that out of it. When we have the function selector, now we can do this switch case against it to try to find which function is called. And it's something like if there's more than 4 functions, I think that's the cutoff. It does a binary search, but if there's 4 or less, it's just a linear search. So how do you get the function selector? Again, the function selector is taking the first 4 bytes out of whatever message was sent, whatever data was sent to the smart contract. The way you do that is to cut out everything but the first 4 bytes via integer division. You can also do bit shifting, but both work. So basically, if you divide the call data, like you're going to load the first 32 bytes of the call data, like the first slot here of the call data. And if you divide out with this number here, you can verify that this actually, this cuts off right at the 4 bytes. Like, it's like integer division, right? It cuts off anything that's after the period, right? So if you do 1 divided by 2, you excuse me, you'll get 0 in that case. But if you do, 4 divided by 2, you'll do 2. 5 divided by 2, what are you going to get? You're also going to get 2, right? Okay, so this selector is returned, and that is it. You got the selector. Once you have the selector, which is returned here, now you're going to switch on that. So is it going to be this value? Is it going to be this value? We don't know. We're going to keep looking for it because the program, like Yule or whatever, the node who's running the Go code, which is geth, is actually looking for which selector you're talking about. So let's say it's this one. Let's say the first 4 bytes of whatever message you sent is actually this, OE8919. That means that you called it with URI and you gave it some uint, some parameter, and you gave it an ID, okay? In that case, it goes to this section of the code and it stops after this. It doesn't keep running through the rest of the cases like other programming languages. It stops right here and terminates, okay? For safety. So, okay, let's say we called this function. What it's going to do is get URI, and it's going to return from and to, and then it's going to return memory data from and to. Okay, so because the URI is a string, the from and to means when does the string start, when does it end. So let's go and see this function. So you see this function get URI returns the URI stored with this ERC1155 token. So all it does is we're going to get the memory pointer. We're going to get the URI length. We're going to say, we're going to mstore where it starts at, which is going to be, OX20 in the return data. And then we're going to get the length. We're going to get and then we're going to iterate here. Look at this. We're going to make an iteration over the URI data from storage. We're going to load it into memory. This loop here, so this is how you write a for loop in Yule. So you do for, you open the curly braces, you define your integers as a starting value. You don't do curly braces in between here, but that's your stopping condition. And then you do curly braces again, which is kind of the increment operation. Like what are you going to do in each iteration to the loop counter? In this case, we're just going to add 1. Note there's no like plus or plus operator. You have to call it explicitly with add. And then what we're going to do here is just we're going to keep incrementing the storage slot from where we want to load the string from. And then we're going to sload that slot we're pointing to right now. That, of course, depends on the length of the URI, right? So if it takes up 2 slots, we're going to go to 2 slots. So we load the slot, and then we're going to get the memory pointer, and we're actually going to mstore where the memory pointer is pointing to, whatever that chunk from storage was. So we just incrementally take a chunk from storage and move it into memory. Maybe this way is better. Yeah. Take a chunk from storage and move it into memory. Another chunk, like the next chunk over, and move it into memory, and so on. Okay? So we just we're copying, we're just making a clone of that piece of storage into memory. And then we keep incrementing the pointer. And now you see why it's so helpful to have this pointer incrementer. It just makes the code much smaller, makes it much more kind of easy to read, I think, because this loop looks like a lot like just a normal loop. Normal by which I mean something you see in Solidity or other higher level codes. And that's it. And then we just store where it ends at. And so we just return that. So we're going to start it here at where the memory pointer is. We're going to end it. And that's it. That's what's returned. So that's pretty easy. Get URI. Then we can do all kinds of other things. We can actually mint an ERC1155. Let's cover that. So if we actually mint one, we're going to decode. These decode functions is just what reads the call data and reads it as a particular variable type. So decode as address means that function. So let's do this. That function means here that we just take the offset into the call data and basically make a check that that the address is in the format as expected, right? That the first 20 bytes is not 0, right? And that there's not a non-zero byte in the rest of the address. So That's all this does. And that's what this does, by the way, right? We're using a mask here where we're basically saying all ones except for the first 20 bytes. And then you're going to invert that so that you have all ones only where you expect an address. You're going to AND that with the actual address. And you're going to make sure through these two things that that is not 0. Okay. You can also decode something as a uint, so you can read something as an unsigned integer, and that's actually used here. So even though it is an address, it looks a little weird, but everything at the end of the day is just ones and zeros, right? Whether it's an address or a uint. So decode as uint just means load this uint, but account for notice that account for the function selector. You want to skip the first 4 bytes. So that's it, really. Anyway, so that's how you get so the way you do the minting is you get the to address first. That sits in the 0th slot of the call data. So that's the first parameter, in other words, of this function. The ID, so which ID do you want to mint? That's the second slot, AK1, because we're 0 indexed. And then also the amount you want to mint. Cool. Now you call the internal mint function. I tried to mimic the actual contract as much as possible in the names and whatnot. But now you mint, this is our internal mint function. And then you do a safe transfer acceptance check. So you just want to make sure that the receiver can receive ERC1155. That's what explains the mocks over here. The no receiver and receiver. And then you emit an event, emit transfer single, 0 address to 2. And the caller was the one initiating it. And then that's the ID and the amount. Okay. And then return nothing. It's just a helper function that just returns 0,0 from memory because nothing is actually returned. All right, let's take a look at the mint function. So let's go here. So the internal mint function, that's where the minting is actually happening. So what it does is it gets the balance of the to address, because the to address is what is being minted to, and that accounts ID. Like, so essentially how many, how many tokens of type ID does to already have? And of course, if it's an NFT, there would only be 1 if they already have it, or 0 if they don't have it. And if it's an ERC20-esque token, right? Remember, ERC1155 is kind of a semi-fungible contract, so it can kind of do both. Then that would just be the amount. That's actually what this is right here. This was the slot, get balance slot. So this is where the actual slot is. Now we S-load that slot, and we get the old balance. And now we're going to add the incoming amount to the old balance because that's going to be the new balance. So again, if they had 100 of some token before, now they're going to have 120, for example, if amount is 20. And then we're just going to store back in how much they have of that. And that's all it is. That's really all what minting is. We're just updating the balance of the to account to be the new. All right. And now we're at it. We see below burn is actually the opposite, right? You just subtract whatever you're doing to the storage. So that's all it is. Okay. Now, and that was the mint, right? That was the mint function. And you can also mint in a batch setting. So you can mint multiple IDs and amounts that are coming in. You just need to be able to load the, these arrays, right? With IDs and amounts. The nice thing is that they are, when they come in, we just need to know the position of them, which we do here, position of the IDs array and the amounts. Once we know those positions, we can just start loading them. So I'll show you. Here, we also have another loop. But basically, we say, okay, what is the len IDs? What is the len amounts? That is the length of the incoming IDs array. That is the length of the incoming amounts array. They better be equal. That's what we're checking here. And then we start looping over them. And basically we say get array element slot. So what this means is go into the position IDs array and load the ith array element, and then decode that as a uint, and that's the ith ID. This is the ith amount. Now go ahead and mint it. Okay, how do you get this element? Well, if you know the array and you know the ith element you want, so this pos array is the position where the size of the array starts. So we know that from the call data because we know the arguments list, right? So we know this. This also means the starting offset is we need to add 32 bytes to the length. That's where the first element starts. Okay. And then we need to divide this by 32 bytes because it comes in chunks. Okay. And then we need to say call data slot offset is add, because, sorry, out here, we're talking, when we talk about we're talking about array elements like 1, 2, 3, 4. But behind the scenes, those are stored in chunks of 32 bytes. So that's why we do the division, because we want to actually like say that is a starting offset. And now, so whatever, let's say it starts at offset, 20 or something, right? Like not 20 bytes, but 20 32 byte chunks. Okay. It could also be 21 32 byte chunks and so on. So we know that the ith element of the array is going to be 22 and 23 and 24. But so we need to talk, because this incoming I is in terms not of bytes, but it's in terms of like which number of which numbered element are you talking about in the array. So that's why we do this division with 20 or with 32 bytes. Okay. A little bit confusing, but it's just a matter of, are you talking about byte-sized chunks because they all have 32 bytes in chunks, or are you numbering them 1, 2, 3, 4? Okay. All right. So cool. That's how you get a dynamic array element from that. So we do that. Okay. Just in the interest of time, I won't cover all of this, but now you've seen minting, you've seen mint batching, which was just a loop over the incoming IDs and amounts, and we just called the underscore mint, like the private mint function, over and over again in the loop. Balance of is pretty easy. You just need to load the balance for that account. But take a look at the code as well in depth. Again, I will keep the video short, but it's very fascinating. There's also the is approved for all that I recommend you definitely take a look at. So basically that is just looking at this function. Great. And all it does is it's just saying, is the operator approved to access all of the account tokens? And it just S loads, so it loads from storage, this get operator approval slot for account and operator. So of course, that's another helper function, which does this. So retrieve the storage slot where approval information is stored, which is a mapping of address to an address to a bool. Okay. And what this does is just it mstores operator approval slot. It then mstores account operator, and then it eventually stores here, or returns it rather. What's the slot? So this is how mappings work in general, by the way, right? This is how you get things in mapping. You need to combine the key with the location of the, where the mapping is stored in storage, right? So the key in this case is operator approval slot owner operator. This is just what I decided. So in other words, it's where the operator approval slot mapping is stored. This is the slot it's stored in. And then you need to append the owner and approver, and that gives you the key. Then you hash the key and you get the slot. And that's where this catcheck is. Notice that catcheck 256, this command only works against memory. So that's why we had to mstore things starting at 0 all the way up to 40. But again, this is starting at 40, so it actually ended at 60. So that's why we need to go from 0 to 60 here. And that's the slot. Cool. So that's it. Again, I'll end it here, but this is how I did an ERC1155. Please take a look at the code if you want. Feel free to clone it. Feel free to give any comments, suggestions you may have. It was a lot of fun to write. It was very challenging, but it gave me a good understanding, much better understanding of ERC1155 at the lowest level, which was also very helpful for other things I was doing at the time and building out. Any comments, please let me know. And thank you very much for watching this video. Hi, everyone. Thank you very much for joining this channel and for subscribing. I hope you enjoy this content. Please feel free to watch the videos and give it a like if you like it, and leave your comment. If in terms of anything you'd like to see differently, anything you'd like to see covered, please do. I'm happy to cover it.